In the autumn of 1967, in the Stanford Artificial Intelligence Laboratory, John Chowning wired one oscillator to modulate the frequency of another and turned the rate up past anything a musician could play. At low rates, that is vibrato, and every player does it. He pushed the rate and the depth far past human limits, doubling and tripling both. Above about 20 cycles a second, the ear stopped hearing pitch change and started hearing a new instrument. The wobble had become harmonics. His account of the moment: I was aware that I was probably the first person to ever hear these sounds, and that what I was hearing was something musical that had probably never been heard by anyone before, at least not by anyone on this planet. Chowning was not an engineer. He was a percussionist who took a doctorate in composition at Stanford in 1966 after 3 years in Paris studying with Nadia Boulanger, who also taught Copland and Philip Glass and Quincy Jones. In Paris, he heard Stockhausen's electronic work, and it set his research agenda for the next decade. That agenda was space, not timbre. Chowning wanted to move sound physically around a listener through loudspeakers. The new instrument was a side effect of that project. Distance cues were the specific problem, and they needed sounds with internal movement. His words: I was searching for sounds that had some internal dynamism. His earliest sounds, around 1964, were computed on an IBM 7090 running a program called Music I Fool, which Max Matthews had sent from Bell Labs as a box of punch cards. Playback went through a PDP-1 using vectorscope converters. By 1967, the work had moved to John McCarthy's AI lab on a PDP-6. Chowning worked off hours when the artificial intelligence researchers were not using the machine. He could not explain why the modulation produced those harmonics. He calls it a discovery of the ear. He recruited an undergraduate mathematics student to work it out, and they found the equations already existed. They were in the radio engineering literature and had been for decades. Frequency modulation was thoroughly understood. Nobody had put both frequencies inside the audible range, because in radio there is no reason to. Chowning did not discover frequency modulation. What he found was that if you tie the modulation depth to an envelope, the harmonic content evolves over the note the way a struck bell or a plucked string does. That is what the 1973 paper teaches, and that is what the patent claims. Stanford's Office of Technology Licensing had to find someone to build it. Its director, Niels Reimers, reasoned from first principles, and in Stanford's own newsletter, he describes the reasoning. Organs play different sounds, I thought. This should be attractive to organ makers. The names usually given are Hammond, Wurlitzer, and Lowry. They came, they listened, they said it sounded good, and they declined. That was a reasonable call. Implementing FM meant designing custom large-scale integrated circuits, and these were analog electromechanical companies. They didn't lack vision, they lacked a semiconductor department. Yamaha had one. That is the entire difference. Yamaha sent an engineer named Kazukiyo Ishimura to Palo Alto. Chowning's recollection: in 10 or so minutes, he understood exactly what I was doing. Yamaha took a 1-year evaluation option in 1973, had a working digital prototype by 1974, and signed the exclusive license in 1975. Yamaha's president, Junichi Kawakami, as quoted in the company's own history: if we can make the best musical instruments in the world, then no matter how difficult it is, no matter how much money it costs, we'll do it. The patent is United States 4,018,121, method of synthesizing a musical sound, filed May 1975, granted April 1977, assigned to the trustees of Leland Stanford Junior University. It ran its full 17-year term and expired in April 1994. It was never invalidated. The license went on to earn Stanford more than $20 million. Chowning's own figure is $22.9 million over the 17 years the patent ran. It is one of the most successful things the university ever licensed. Chowning, on what the money bought, it has meant a lot for CCRMA. It's helped us to maintain computer music at a level we certainly couldn't have otherwise. In that same newsletter, in 1994, Chowning writes, "I never realized PM would be so successful." PM, not FM. Because what Yamaha shipped, and what the industry has called FM for 40 years, is technically phase modulation. The silicon modulates the index into a sine table rather than the frequency directly. Mathematically adjacent, audibly similar, and not the same thing. The first attempt was the GS1 in 1981, 90 kilograms, 2,600,000 yen. To edit a sound at all, you needed a separate external programmer. It sold roughly 100 units. 2 years later, the same technology, 1/10 the price. The DX7 shipped in May 1983 at $1,995, about $6,400 today. For comparison, in the same shops, a Roland Jupiter 8 was $5,295, a PPG Wave, $8,800, an EMU Emulator 2, $7,995. 16 voices, velocity and aftertouch, MIDI at roughly a third the price of the cheapest thing near it. The reason is 2 chips, the YM21280 operator array and the YM21290 envelope generator. The GS1 had needed something like 50. FM was cheap in a way subtractive synthesis could not be. Subtractive synthesis needs a filter per voice, and in 1983, an analog filter was board space, trimming, and temperature drift, multiplied by however many notes you wanted to play at once. FM needs no filter at all. All of the timbre comes from arithmetic. There is nothing to trim and nothing to drift. Yamaha went further than that. The DX7 does not have 6 oscillators, it has 1, and it computes each operator in sequence, 96 clock cycles per sample, 6 operators across 16 voices, running at just over 49 kilohertz. Above CD rate in 1983 from 2 chips. Storage is shift registers rather than RAM, so bits physically circulate, which imposes a discipline. Every computation path must take exactly the same number of cycles as every other one. Arithmetic is done in the logarithmic domain, so that amplitude scaling becomes addition, because multipliers were the expensive thing. The sine A table is a quarter period, delta encoded, exploiting symmetry. The 32 algorithms are a small lookup table, not 32 circuits. Enormous configurability at nearly no cost in silicon. The 32 are an editorial decision. The space of possible 6 operator routings is vastly larger. Yamaha curated it. Even the output stage is a trick. A 12-bit converter, time multiplexed with 2 sample and hold circuits, and an amplitude scale factor, producing roughly 15 bits of effective resolution. They faked 15-bit audio out of 12-bit parts. Every one of those decisions made the machine cheaper, and not one of them maps onto anything a musician can see or feel. A Minimoog's front panel is a picture of its signal path. The DX7's front panel is a picture of nothing. Flat membrane buttons with no travel. One small LCD showing 1 parameter at a time. No knobs for roughly 145 parameters. And those parameters are not independent. Turn up an operator's output level, and you have not changed its volume, you have changed the modulation index, which means you have changed the entire harmonic content of everything it feeds. There is no such thing as a small edit. Worse, sideband amplitudes follow Bessel functions, which oscillate. Turning a parameter up can make a partial quieter. The instrument violates the one property interface design depends on, which is that response to input is predictable. So Yamaha shipped 128 finished sounds. They were programmed by David Bristow in the UK and Gary Leuenberger in the US, and by Bristow's own account, the job quadrupled in size shortly before the keyboard went into production. One of them was called E-Piano 1. It was an imitation of a Fender Rhodes. The musicologist Megan Lavengood went through the 1986 charts. Her published figures, E-Piano 1 appears in 39% of the Billboard Hot 100 #1 singles, 40% of the country #1s, and 61% of the R&B #1s. That number deserves care. Lavengood identifies the preset by ear from a list of chart toppers, expert oral identification, not an instrumentation database. There is no documentary proof. It is the best evidence anyone has, and nobody who works in this music disputes the direction. Players abandoned actual Fender Rhodes pianos for a synthesized imitation of one. Lavengood's framing, musicians treated DX7 presets the way people treat auto-tune now. Everyone used it, nobody admitted it. Roland Orzabal of Tears for Fears, more directly, stop using bloody DX7 presets and invent something new. FM's run at the top lasted 4 years. The Roland D50 in 1987 spliced short sampled attack transients onto synthesized sustains, matching FM's best trick without requiring anyone to understand Bessel functions. The Korg M1 in 1988 finished the job. The mechanism was simply that memory got cheap. FM's entire value proposition was convincing timbres without storage. Once you could store a recording of a piano, you did not need to compute an approximation of one. FM lost on ease, not on quality. The same property that cost FM the high end gave it a second life. A computation needs no ROM, so FM went down market into chips. The YM3812, OPL2, 1985, the Adlib card, then Sound Blaster. The YM2612, 1988, the Sega Mega Drive, the YMF262, OPL3, 1990, Sound Blaster Pro. For most of a decade, the default sound of a personal computer game was a composer's 1967 accident, discovered while trying to move sound around a room. It rhymes with the 808. The YM2612 has a low-volume distortion artifact caused by an amplitude error in the die. The corrected YM3438 removes it. Chiptune musicians prefer the broken original, because that distortion is the Mega Drive's sound. Chowning received a technical Grammy in February 2026 at 91. He called it an award I never sought and noted that most Grammys are given to people who would love to have one, performers. He also rejects the title composer. I'm not a composer, I'm a musician who loves to compose using computers. And on what the technology did, he is unambiguous. I'm proud to be associated with it because it democratized computer music. A composer looking for a way to move sound through space found a way to make bells out of arithmetic, and Yamaha turned it into the cheapest possible silicon. The sound the world reached for most was an imitation of an electric piano, played by people who could never have afforded the real one.